So I will remind you, Ronak, around 25 minutes.
Thanks a lot.
Okay.
Yeah, thanks a lot. Thank you, Shibaji, and thanks to the organizers for this wonderful conference and for inviting me. So I will talk about this paper I wrote with this set of people, and it is. So let's start with what the talk is about. Okay. Yeah. So this talk is really about the entropy of de Sitter space. So in ADS CFT, the Bekenstein-Hawking entropy of a black hole has an obvious interpretation. It is the number of CFT microstates in the dual CFT. Okay, but the corresponding entropy of de Sitter, which is the Gibbons-Hawking entropy of the cosmic horizon, does not have such an interpretation, and this is the problem we will tackle. So to set the stage, I have drawn some pictures of the eternal black hole in ADS and de Sitter to remind you of what's similar and what's different. So the first picture is the Penrose diagram of the eternal black hole. As you can see, as you go outward in a space-like direction, the radius of the internal circle diverges, and as you go be inside the horizon, you hit a singularity where the radius goes to 0. Okay, de Sitter has the same Penrose diagram. Okay, but in the exterior, the radius of the circle goes to 0, and in the interior, it diverges. Okay, so it really looks like the same Penrose diagram flipped 90 degrees, and both of them have horizons, but these horizons are very different in some ways. So to see the difference, we'll look at a Cauchy slice of these two diagrams. In the black hole case, the Cauchy slice looks like a throat, and the horizon is the neck of this throat. Okay, and in de Sitter, the Cauchy slice looks like a sphere. Okay, and the horizon is the bulge of the sphere. This is called the cosmic horizon, and we will also call the corresponding opposing points the poles. If the cosmic horizon is the equator, these are the north and south poles. So this cosmic horizon is the guy whose entropy we will be talking about. And the main result of this talk is that at leading order in small g Newton, strictly leading order, we will give a South state counting interpretation for the Gibbons-Hawking entropy in 3D de Sitter space. The way we will do this is by relating the black hole and cosmic horizons using the TT bar plus lambda 2 deformation. Okay, so let's more of an introduction to the Gibbons-Hawking entropy. So taking a de Sitter 3 with de Sitter scale L, the cosmic horizon has a Gibbons-Hawking entropy, which is area by 4g Newton. Surprise, surprise. The area, because de Sitter, we are in de Sitter 3, the area is the area of a circle, and so it's just 2 pi into little l, where little l is a de Sitter radius. Okay. Now, this is a very old observation dating back, I believe, to the 80s. The new thing that was added in 2018 was that this value has a very interesting connection to CFT. So, assume that there's a number C, which is 3L over 2G Newton. This formula, 3L over 2G Newton, is the Brown-Hanover formula for the central charge of a CFT dual to ADS. But de Sitter, of course, does not have a dual CFT. So here C is just some formal number. It turns out that the Gibbons-Hawking entropy is the number of states in the CFT at a given level, at a given conformal dimension, without spin. Okay, and the formula that counts the number of states in the CFT is called the Cardy entropy, and without spin it looks like this. And if you put delta equals C over 6 and plug in this value, you get this value. Okay, and yeah, so, and the delta is not just any level. It is known as the Hawking-Page level. It is dual to the smallest BTZ black hole that is canonically stable. Canonically stable means that this black hole is a dominant saddle in the canonical ensemble. Okay, So it's a very special level in ADS. It's not just any level. And today we will argue that this is more than a coincidence. Okay, so one of the main ingredients we will use is what's called modular S invariance. So consider a QFT partition function on a torus with no spin with the whose spatial cycle has length 2 pi r and whose time cycle has length beta. But notice that when I say this is spatial and this is time, that is completely meaningless because the torus is Euclidean. I might have called the second time and the first spatial. Okay, and this fact that there is no special time cycle goes by in some sense a symmetry of the partition function written here, and is known as modular S invariance. Though the partition function, which is a number, is the same no matter what you call time, there is something special about time because eventually we will want to Wick rotate the time and go to Lorentzian space, and then it matters whether we are looking at this or that. And this I have illustrated here. So I've taken a case where beta is much bigger than 2 pi r. So the equality is that this partition function and this partition function are the same. Okay, but when we Wick rotate, we get two different states. In this case, we get a state on two thin cylinders with low entanglement. And in this case, we get a state on two thick cylinders with high entanglement. And states created by these half semicircle path integrals are called thermophile double states, as I'm sure most of you know. So let's say a little more. Let's now specialize to holographic CFTs. Now we will work with holographic CFTs that are dual to pure gravity, quote unquote. There are no such CFTs, but we will take this approximation, and the fact that we work in this approximation is a big footnote to the results of this talk. Okay, what does it mean to be dual to pure gravity? It means that the only primary of dimension less than order C is the stress tensor. We do not actually know of a single CFT with this property. There is some evidence that averages of CFTs can have this property, but I don't know if the question has been settled. Okay, so in these cases, the partition function actually looks really simple. Minus log z looks like the minimum of two terms. In this equation, evac is the energy of the vacuum, and evac of 2 pi r is the energy of the vacuum on a circle of length 2 pi r. Okay, so you can see that the two terms correspond to the vacuum on 2 pi r propagating along the beta cycle, or the vacuum on beta propagating along the 2 pi r cycle. This is the minimal form consistent with modular S invariance, and it turns out that this formula has an extended range of validity for holographic CFTs, which was shown by this paper here. Okay, and the Hawking-Page transition is nothing but the transition between these two saddles, and as you can just by eyeballing this formula, this transition happens at beta equals 2 pi r, right? Because that is a symmetric point. So when beta is greater than 2 pi r, we are in a low temperature phase. When beta is less than 2 pi r, we are in a high temperature phase. The low temperature phase and high temperature phase, when we go to the corresponding Lorentzian thermophile double and look at the bulk dual geometries, have a very nice form. The low temperature phase is what's known as thermal ADS. It's two copies of vacuum ADS with entangled bulk fields. The high temperature phase, it just looks like a two-sided eternal black hole. And this can be, and this was the original Hawking-Page transition. Hawking and Page's paper was about this transition. And later with ADS CFT, people understood more about the CFT dual of this. So the thermal ADS saddle, of course, gives a contribution, which is beta into evac of 2 pi r, which is the vacuum propagating in the direct channel. And the BTZ saddle, so this is a BTZ black hole, looks like the vacuum propagating the cross channel, which can also be written in the thermodynamic form as minus the Cardy entropy at some conformal dimension delta, plus the plus some excited state propagating along the beta channel. And right, and this conformal dimension is related to beta and 2 pi r by this equation. The details are not so important, but notice that at the symmetric point, this becomes C over 6, which is the level we saw earlier. And of course, when beta is less than 2 pi r, then the number increases, the conformal dimension increases. So this is the smallest conformal dimension for which the bulk is a black hole. And the corresponding horizon radius, so RH is the radius of the horizon, is just the ADS radius. Okay, so this is the Hawking page level. Okay, so this is the by quick introduction to Hawking page transitions. So this is so we actually have now spoken about all the three things that are turned up in the title. We are going to go from the Bekenstein-Hawking entropy to the Gibbons-Hawking entropy via the Hawking page transition. Okay, and so what I've told you so far is about pure de Sitter or purely holographic CFTs. The way I will relate these two different systems is via the TT bar plus lambda 2 deformation. The TT bar plus lambda 2 deformation is a deformation of a 2D CFT defined by a differential equation of the partition function. The differential equation is given here. There is a parameter lambda. When lambda goes to 0, you end up at the CFT. Morally, the first term in the differential equation is determinant of the stress tensor, which is also known as TT bar. And the second term is just an integral of 1. And both the determinant of stress tensor and 1 are special operators in that they exist in a large class of theories. The fact that determinant exists in a large class is a very non-trivial fact proven in this paper over here. Now, notice that we said lambda is a deformation parameter. So we want to turn it off and get the CFT partition function. But here, if you look at this, this is not generically possible because there's a lambda in the denominator. Why is there a lambda in the denominator? Dimensional analysis. Lambda has dimensions of length squared. An area has dimension of length. The left-hand side has dimension of 1 by length squared. So you need a 1 over lambda squared to make up the difference. Right? So only when eta equals 1 can you send lambda to 0. Otherwise, this lambda 2 term diverges. So we start with this as a boundary condition, that when eta equals 1 and lambda equals 0, we get the CFT partition function. Now, then to define the theory for eta not equal to 1, we have to do something else. And for this, we make the following observation, that this lambda 2 term becomes unimportant when little lambda goes to infinity. Right? And so we say that no matter what eta is, it flows to the same value at little lambda equals infinity. So this is our definition of the theory. We have a differential equation and we have boundary conditions. Okay. Cool. And this is a solvable theory in the sense that we can find in all the energy levels on a circle of radius r, and they look like this for eta. Here I have defined a dimensionless combination lambda hat, which is lambda over the radius squared. And as you can imagine, everything important is encoded in lambda hat, not in lambda itself. So here delta minus C over 12 is the conformal dimension minus the Casimir energy of the vacuum. Minus C over 12 is, of course, the energy of the vacuum in CFT. And the thing to notice about this formula is that it has a square root. And square roots famously are not necessarily real. So what are the conditions for reality? So suppose eta equals 1 and delta is greater than C over 12. Okay, then lambda hat has a maximum value. So notice that this is very weird because we just said that we are interested in lambda hat going to infinity. But here for delta greater than C over 12, there's a maximum value. But this kind of makes sense because if you set eta equals -1, say, or 0, the square root is only real if delta is less than C over 12, right? Because the second term has to be positive. And now lambda hat has a minimum value. So it all makes sense. Clearly the eta not equal to 1 theories are very weird in that they have very few states. Say eta equals -1 theory, because delta has an upper bound, which is C over 12. This we can understand from the bulk as well. So for eta equals 1, this deformation takes a holographic CFT to the quote-unquote dual of finite cutoff patch of ADS3 with Dirichlet boundary conditions. So in the vacuum ADS, the CFT is dual to the entirety of vacuum ADS, but the deformed theory might be dual to just the blue region, or in the black hole, or for a black hole pure state, this blue region, where this is the horizon, and this is this line here is a cylinder, and yeah, so everything between the horizon and the boundary cylinder. Okay, this piece here, by the way, is where we assume that the CFT is dual to a pure gravity theory, and one hopes that one can correct this assumption with the in perturbation theory. But for this talk, we will stick to the regime where this is exactly true and CFT is exactly dual to pure gravity. Cool. And the size of the cylinder, the radius of the cylinder, is given by 1 over root lambda hat. This is 4GNL is some factor, and the stress tensor is given by the extrinsic curvature on the boundary of the blue region, right? And this G mu over L gives you the uninteresting one part in the energy formula here, and the square root comes from the part dependent on extrinsic curvatures. And the upper limit on lambda hat we can now understand as the Dirichlet wall hitting the black hole horizon. Okay, because as lambda hat increases, capital R decreases, and at some point capital R will hit the radius of the horizon. This is for eta equals 1. For eta equals -1, we will, for general eta, the theory is dual to a bulk theory. The 2D theory is dual to a bulk theory with this cosmological constant, which is proportional to minus eta. So for eta equals -1, the cosmological constant is positive, and we have de Sitter. Okay, and the effect of lambda 2 disappearing when little lambda went to infinity was the same as saying that this cylinder here becomes really thin, so the inside looks flat. And so, and the point is, when you zoom into any space very close, what you have left looks flat. And that is the reason that the deformation looked universal in that limit. And yeah, so we use the boundary condition we mentioned earlier of batching at really small cylinders to define the theory in de Sitter. Okay, and now the upper limit on delta also makes sense, because in 3D there are no black holes when lambda 3 is positive. Okay, so anyway, after all the dust has settled, we have a theory dual to the orange region here. This is again a cylinder, and we call this region the pole patch. And the minimum of lambda hat that we mentioned earlier is when this pole patch boundary hits the cosmic horizon. But notice that the cosmic horizon is not included in the bulk. Okay, so this is kind of dissatisfying. There's no, it's all consistent, but the interesting part, the part that has all the entropy, is not included in the theory. But so this was the situation for a while, till this paper by Vasudev Shyam came out, which found an actual inconsistency, where he showed that the torus partition function of the de Sitter theory at high temperature gave us a thermal entropy. Okay, gave us the Gibbons-Hawking entropy. So we have a theory without a cosmic horizon, which has the entropy of the cosmic horizon. Not only is this weird, this is inconsistent, because as I mentioned, the number of states of delta less than C over 12 do not scale with G Newton. They're order G Newton power 0. But this entropy is order 1 by G Newton. So there's much more entropy than states. And this is a torus partition function. It should have a state counting interpretation. The method he used to prove this was that he assumed modular S invariance. And he took the partition function to be just the contribution coming from the vacuum propagating the cross channel, the high temperature contribution we mentioned earlier. From here, you take the derivative, you get the entropy. So let's try to understand this in the bulk. So the pole patch we mentioned earlier has a metric of this form. This is Euclidean. The time has periodicity because it's Euclidean and it's a partition function. And yeah. And rho, which is the rho has a includes the pole which is at rho equals 0 and has an upper limit. Now we do a modular S transformation, which means we exchange space and time, and we define R as the radius of the new spatial circle, which turns out to have this value. And after the dust settles, we end up with the same metric with some renamings, but with a different range of R. Now R goes from some minimum value to L, and R equals L was the cosmic horizon. So here we had a theory, we had a region without the cosmic horizon, we did a modular S transformation, and we found the cosmic horizon, which is similar to what Vasu did. And in pictures, it's easier to draw in Lorentzian space. The original theory, the thermofield double looks like this, just two copies of the pole patch. We do a modular S transformation, we get a region including the cosmic horizon. So this is why the S invariant theory had horizon entropy. It's because it has the horizon. And basically the point is that new states were added. The assumption of S invariance was not innocuous. It actually did something non-trivial. Okay. And one thing you notice is that if you calculate the energy using the extrinsic curvature in this phase, you get something that is just not included in the previous set of energy levels, which again goes with our intuition that new states were added. Okay, So I see I'm running out of time, so I'll be a bit quick. I just have a few more slides, so I'll just wait for the question if you don't mind. Basically the point is that now we have to look for new energy levels, and the way we look for new energy levels is we find a new boundary condition for the eta equals -1 partition function. And we noticed from the differential equation, where is it? Yeah, that we could have put a boundary condition of this form for any non-zero value of lambda, because this only diverges at lambda equals 0. Right? So, is there such a nice non-zero value of lambda that we care? That looks nice. The answer is that basically it's when the Dirichlet wall hits the horizon. And this is because just like when we zoomed into vacuum areas, we got flat space. When we zoom into a horizon, generally we get Rindler horizons. Okay, so this is a small calculation showing that whenever you go to a near horizon region, you get a Rindler horizon. You get Rindler space. And so we just take lambda naught as corresponding to the limit in which the boundary of ADS hits the horizon of some particular black hole. Now, which black hole? Now, when we actually get the near horizon metric to be Rindler space, we find that the circle has a specific radius, which is not open to us. It depends on where the horizon is. So we have to match the horizon radii across the transition. And since we are interested in the cosmic horizon, whose radius is L, we choose a black hole with the same radius. This radius, as we have seen before, it is the radius of the black hole dual to the Hawking page level. Okay, so I've written down
5 more minutes.
Yeah, thank you. Good. So I've written down the flow here. So the wall to horizon limit, as I mentioned earlier, is the one in which the square root of the energy formula vanishes. Okay, so this is the square root of the energy formula for eta equals 1, which is ADS. And as you can see, we replace delta equals C over 6, which is the Hawking page level here. And so that gives you a certain value of lambda hat naught where it vanishes. So our rule is we start with the CFT energy at this level. okay, which is this. We do the eta equals 1 deformation to lambda hat naught. We get this energy. We now flip eta to -1 and keep increasing lambda hat. And then we get this energy. And this energy is exactly what we found from the high temperature phase in the partition function. Okay. So now for node, we can do this for every energy eigenstate here. How many energy eigenstates are there? A Cardy entropy worth, right? So we end up with a Cardy entropy worth of energy eigenstates here. But we already mentioned the Cardy entropy at this level is the Gibbons-Hawking entropy. So now we found the right number of states dual to a region with the cosmic horizon in it. This is a state counting interpretation of the Gibbons-Hawking entropy. Now this is the main result. So let me add 2 footnotes. One footnote, as I mentioned earlier, is that we assume the existence of a CFT dual to pure gravity. Where our hope is that we can go beyond this in perturbation theory. The other footnote is that we don't actually know that much about the microstates of a given black hole. You know, we just know some very coarse-grained stuff like the number of microstates. So the actual statement is, if some magical elf came and gave you control over all the microstates of the black hole, you would be able to play with those microstates and get microstates of the cosmic horizon. So I will skip these 2 slides. So I told you here the deformation for a given level. One can ask about other values of delta, and it turns out that there are 2 proposals that we found, and both of them agree at the right value. But I will skip over that to the summary. So again, we defined the TT bar plus lambda to flow of a 2D holographic CFT, quote unquote, dual to pure gravity, that deforms the black hole microstates at delta equals 0.6 and ends up with giving you a state counting interpretation of the Gibbons-Hawking entropy. To summarize what we did, the original flow was taking the CFT, doing TT bar to large lambda, and then going backwards with eta by adding the lambda to term. TT bar, of course, is just the eta equals 1 deformation because the lambda to term vanishes. And this gives you states dual to the pole patch, and there are only order 1 number of states. You do an S transformation, you end up adding new states dual to a region considering the cosmic horizon. And the deformation that gives you this is you take the CFT, you do TT bar to a finite value, and then add a lambda to term and keep increasing lambda. These 2 flows look like they have nothing to do with each other, but it turned out that this flow plus modular S invariance forces you to have this flow. Okay, and there are 2 extensions to other levels. So this I have actually defined this flow only at delta equals C/6. At other levels, there are 2 possibilities, and we discussed them in the paper. I did not discuss them today. So I'll just tell you some further questions. One question is whether we can reproduce log corrections. For that, we require spin, as actually Ashok showed in a paper from a while ago, that the log corrections to black hole entropy or and also Gibbons-Hawking entropy require including spinning states. And today we set spin exactly to 0 everywhere. The other question, of course, is higher dimensions, which is more interesting. And then a natural question that appears when you start thinking about higher dimensions is that today we saw that the black hole horizon became the cosmic horizon. And there's a reason for this, because in 3D, de Sitter just doesn't have black holes, right? In higher dimensions, does the ADS black hole horizon become the cosmic horizon, or the black hole horizon of de Sitter, or either one depending on mood? This is an interesting question. Actually, we don't know the answer yet. Third one is adding matter, which is going beyond the dual to pure gravity assumption I mentioned earlier. And the reason this is hard is because earlier I just very cavalierly changed eta because it's just a classical solution. But in the case of matter, changing eta becomes a matter of changing the vacuum. And this is a kind of non-trivial step. So we don't know everything about what is required for this. Fourth point is that now we have a thermofield double, including the cosmic horizon. So once you have thermofield doubles, lots of papers have been written about the thermofield double in ADS. All those papers can be written with the flip of the cosmological constant. And immediate question is calculations of entanglement and quote unquote top complexity, which is something I'm working on with Evan Coleman and Sangyan Yang. Hopefully we will put up the paper soon. The second one is the last point is thinking about how to get the entirety of the sitter, not just one patch of it. And the broad idea is to take two copies of the partition function and integrate over the boundary metric in some way. So that one copy gives you the hope is that if one copy gives you this region and one copy gives you that region, and we're able to integrate over the metric of the joining region, we might get a theory where metric everywhere is dynamical, including here. And it includes all of the sitter. We tried some ideas, it didn't quite work. Yeah, this is the last question. And with this, I would like to end my talk. Thanks a lot. And I believe Somdatta had a question that I rudely said no to. Thanks a lot.
Okay, thank you, Ronak. We have time for one or two very quick questions. I can see hands, Somdatta. If it is a quick question, you can ask. Otherwise, you can go to discussion session.
It's a quick question. Could you go back to your first slide where you had the Penrose diagrams for the de Sitter? Yeah. So the poles mean that, does the pole mean the right pole, does it mean that it's a initial singularity?
No, this is a Cauchy slice here. So these two poles are here and here. Like these are spatial slices. So de Sitter, the spatial slice really looks like a sphere.
Spatial slices, but the Penrose diagram has to have time, right?
Oh yeah, but sorry, this is the Penrose diagrams.
Yeah.
This is the
So in the
slices.
Penrose diagram, the R equal to 0, what does it indicate? What does it mean? What does it mean to have R equal to 0? Does it mean that
so R is no, it's at the space. It's not initial because it's first of all it's at to get to that from any bulk point you need to move in a spatial direction, and secondly it's not a singularity because basically you can look at the metric and it's smooth. What R equals 0 means is that basically some internal space is shrinking. In de Sitter 3 case it's a circle, and any internal space can shrink in either a smooth way or a non-smooth way. In ADS, at the singularity here, it shrinks in a non-smooth way. Here, it shrinks in a smooth way.
Yeah. So in any case, it's okay. I'll talk in the discussion session.
Okay.
Maybe we can.
Are there any other questions? If not, let us thank the speaker again. And thank Ronak for a nice talk. And the next speaker is Siddharth Prabhu from ICTS Bangalore.